Hello everyone, this is Firoz Nadaf. I welcome all of you to my YouTube channel. I am going to show you design of doubly reinforced beam through Microsoft or WPS Excel. Before seeing the video, you must have a little bit knowledge of manual design of doubly reinforced beam as well as singly reinforced beam. You see, Excel are used as a tool to ease the calculation procedure, to ease the calculation of the design or calculation of anything for that matter. While making the sheet, you have to make some effort for formatting, for inserting formulas at the required places. This video is going to be long because many things need to be covered while designing a beam through Excel. Once the sheet is ready, then you only have to place the input and you will get the required output. But while you making the sheet, you have to give some time for making the sheet. Here you see the beam shall be designed for flexure as well as for shear, means a complete design of beam shall be showcased here. These are the given data for which a beam shall be designed. A doubly reinforced beam shall be designed. Column C gives you the different terms that are used in the design, like width of the beam, clear span, overall depth of the beam, and those terms are indicated by some symbols which is given in column D, like small b is the width of the beam and capital D is overall depth of the beam, small w is the superimposed load that is acting on the beam, and column E gives the magnitude of different terms and F gives the unit of these terms like mm, meter. You see, to write mm in the Excel is easy, you can easily write mm, but to write something which is superscript and subscript, that you have to take care. For example, if I want to write mm square, I'll just select this term and right click and go to format cell, and a window will appear in the screen, and you just have to check in superscript, subscript, whatever the things you want. Here I want superscript and I will press on OK, and here I am getting superscript. So if you want to add subscript, same procedure has to be followed, but in that you have to check in on subscript. Now we will see how to find effective depth of the beam. Effective depth of the beam is denoted by small d. It's a distance from top of the beam to the center of the reinforcement. We need to understand the dimension of effective depth in order to understand the formula. After understanding the formula, we have to insert in one of the cell. Okay, so I will just show you what is effective depth. This is the cross section of the beam, and here I am showing the reinforcement. So this beam has reinforcement at the top as well as at the bottom. Okay, so and you see, if you are very clear with the detailing part of the beam, you will understand that the beam is having shear reinforcement. It is also called as stirrups or ring. Okay, normally the ring that we provide in the beam is of 8 mm. Normally we provide, it can also be of 10 mm. It depends on the design for shear reinforcement. Okay, so you see, what is the effective depth? Effective depth is a distance from top of the beam to the center of the bottom reinforcement. Center of the reinforcement. Okay, and you see, this is the overall depth of the beam. Capital D is overall depth of the beam. So small d equal to capital D minus this distance. This distance is nothing but it's a clear cover, and we have to take clear cover from the IS code. It depends on the exposure conditions. So here we have taken 25 mm as clear cover. We can write clear cover minus the diameter of the ring. You have to deduct the diameter of the ring, or stirrups, and then half of the diameter of the reinforcement. Whatever reinforcement that you will provide at the bottom, half of the diameter of that reinforcement shall be taken in. half of the diameter of reinforcement, or we can simply write pi by 2. Okay. Now we will insert formula here. I'll show you. I will write here effective depth of the beam. Effective depth of the beam. Okay, it is indicated by small d. Here I am inserting the formula equal to. Whenever you are inserting formula in the cell, it has to be start with equal to sign. Okay, equal to capital D, that is E13 minus clear cover, that is E10 minus diameter of the ring. Directly I will take 8 mm because most of the time we provide 8 mm only, and then half of the diameter of the bar. So initially in the Excel you have to assume what diameter of the bar you shall be providing. Okay, so here we are assuming diameter of the bar as 25 mm. Okay, so you can take in bracket divided by 2, bracket close. Okay, so this is the effective depth of the beam. You can write mm. Now we will see effective span of the beam. It is denoted by L effective. IS 456-2000 has given two formula by which we can calculate effective span of the beam. After calculating the value of effective span of the beam by using both the formula, we shall take least of the two value. I will tell you what is that. The first formula is L effective equal to clear span plus effective depth. Clear span is given in the given data. It's given in the problem statement. This is the first formula. Second formula is L effective equal to center to center distance between the support. So we have a beam, we have this beam, and this beam is supported on some support and it has some width. Okay, so the width of the support is given in the problem statement, that is 500 mm. 500 mm. Okay, so the next formula states that L effective is nothing but center to center distance between the support, and we know the clear span, and if W is the width of the support, so distance from this point to this point will be W by 2. Okay, so L effective equal to clear span plus W by 2 plus W by 2. Either side you have W by 2, W by 2. You can rearrange the formula L effective equal to clear span plus W. W is width of the support. Now we will see how to incorporate this in the Excel. First is clear span. Clear span is in meter. Okay, clear span is in meter plus effective depth. You see, effective depth is in mm. We need to convert mm into meter. We can do that. Effective span divided by 1000. Sorry, effective depth divided by 1000. We'll get some value. This is effective span by number one formula. Number two formula is center to center distance between the support. We have rearranged the formula. We know what is the formula. Clear span plus width of the support. Okay, again you see width of the support is in mm and clear span is in meter. Mm has to be converted into meter so that effective span will be in meter. Clear span plus width of the support. You can take bracket width of the support divided by 1000, enter. You are getting 6.5. So what we need to consider? We need to consider least of these two values, and one function is there. That function is called as minimum function. Automatically it will take the minimum of the two. Minimum function, this, and you have to select the variables. These two variables I am selecting, and automatically it shall take the minimum value or the least value out of those two values. Okay, so we are getting here L effective equal to 6.455. Here I am getting the value of L effective up to 3 digit. I want the value up to 2 digit. In that case, what I have to do, I have to use the roundup function, and I have to specify how many digits I want. I can use roundup function with minimum function also. Roundup function can be used with any function for that matter. I will just add roundup, and I will specify here 2 digit, comma 2, bracket closed. Here I am getting L effective 6.46 up to 2 digit. Now we will see factored bending moment and shear force. Beam shall be designed for bending moment as well as for shear force. You see, beam it shall be designed for the load acting on it, that is the superimposed load plus self weight of the beam. It has to retain the superimposed load as well as the self weight of the beam. So before going towards the calculation of bending moment and shear force, first we need to finalize the total load of the beam plus that is superimposed load plus the self weight of the beam. And here I will tell you how to calculate the self weight of the beam. Self weight of the beam, we have one formula to find the self weight of the beam, that is B into capital D into density of the concrete or density of the RCC. Density of the concrete, normally we take 25 kilonewton per meter cube. This is the density of the concrete, and you see the B width of the beam is given, overall depth of the beam is also given in the problem statement. The B is given in mm, D also is given in mm, and the density of the concrete we have in meter cube. Okay, so we want the weight in kilonewton per meter. For that we need to convert mm into meter, and we can do that by dividing it by 1000. Divide B by 10 raised to 3, divide D by 10 raised to 3. So whole thing you have to divide by 10 raised to 6. Okay, so this is the formula, B into capital D into 25 divided by 10 raised to 6. This formula you have to insert in the cell. Okay, I will do that. Equal to B is 300 into, you can also edit the formula in the formula bar. D is overall depth is 500 into 25. Okay, divide the numerator by 10 raised to 6. You will get the value of self weight of the beam, that is 3.75 kilonewton per meter. After getting self weight of the beam, we have to find the total load on the beam or total load of the beam, a load for which a beam shall be designed. It is self weight of the beam plus the superimposed load. Okay, so you see, I will write here the load acting on the beam is the self weight of the beam, its self weight plus superimposed load or the load coming on the beam. Okay, so the superimposed load is given in the problem statement, and we have calculated the self weight of the beam, that is 3.75 kilonewton per meter. Superimposed load is also in kilonewton per meter. So we get a UDL, the total load is the UDL. We need to add superimposed load plus self weight of the beam in order to get total load. But when you are designing by LSM, the total load will be multiplied by load factor. Because in limit state method, we need to take factor of safety with respect to the load, that is called as load factor, and the load factor depends on different conditions. Normally we will take it as, in manual design, we shall take it as 1.5. So whatever total load you shall get by adding self weight of the beam plus superimposed load, that load has to be multiplied with load factor, and the load that you will get after multiplying with the load factor, that load will be called as factored load, and beam shall be designed for the factored load. I will show you how to do that in Excel. Factored load equal to 1.5, this is the load factor, multiplied by bracket self weight of the beam plus the superimposed load. Self weight of the beam plus superimposed load, bracket close. You are getting the factored load or total load for which a beam shall be designed is 50.625, and you can round up this value up to 2 digit if you want. I shall use roundup function. Okay, here comma 2, I want up to 2 digit. So I am getting the total factored load 50.63 kilonewton per meter. You see, we have to design a simply supported beam, and this simply supported beam is subjected to UDL over the entire span. The intensity of UDL is 50.63 kilonewton per meter. That is nothing but the factored load which we have calculated, and the span is the effective span of the beam, which we know, that is 6.46. Okay, so for this arrangement we have to find the bending moment and shear force, and whatever bending moment we shall be calculating, it will be called as factored bending moment. In the same way, the shear will be called as factored shear force. Okay, now you see, we have to find the maximum bending moment and maximum shear force for this arrangement. For this arrangement, we know the formula of maximum bending moment, that is WL square by 8. L is the effective span of the beam, W is this 50.63 kilonewton per meter. Shear force is WL by 2, which is at the end. We know for simply supported beam, the end of the beam will have maximum shear force. Now we have to see how to incorporate these two values, the bending moment and the shear force, in the Excel, to find bending moment and shear force through Excel. Factored bending moment equal to WL square by 8. W is 50.63 into L is 6.46 into 6.46. You can do in that way, 6.46 into 6.46 divided by 8. Here you are getting maximum bending moment. The unit of the bending moment is kilonewton meter. We also have to find the factored shear force. We know the formula, factored shear force, that is WL by 2. WL by 2, L is the effective span of the beam. W is 50.63 into L divided by 2. The unit of shear force is kilonewton. Now we will see design factors. Whenever we are designing any structural elements with respect to limit state methods, we are required to write some design factors. Here also we have some design factors. We are dealing with the design of beam. Design factors are xu max by d, xu max by d, then you have q li m, and then you have then you have mu li m. xu max is the limiting depth of neutral axis, d is the effective depth of beam, QLM is moment of resistance factor for limiting section, MULIM is the again it is the moment of resistance for the limiting section. Okay, we will see how to write the formula for xu max by d in the Excel. For that we have to recall what is the formula of xu max by d. The formula of xu max by d is xu max by d equal to 0.0035 divided by 0.0055 plus 0.87 Fy divided by Es. Okay, so here Fy is the grade of steel which we have indicated in the given data, and Es is the Young's modulus of steel. We know the value of Young's modulus of steel, that is Young's modulus Es equal to 2 into 10 to the power 5 Newton per mm square. And you see this value of Young's modulus of steel, it remains constant. So whatever the grade of steel that you will be using, whether you are using Fe 250, if you are using Fe 415, 500, the value of Young's modulus of steel does not change. It remains constant. So since it remains constant, we can substitute the value of Young's modulus here, and we shall rearrange the formula. xu max by d equal to 0.0035 divided by 0.0055 into Es plus 0.87 Fy divided by Es, and this Es we can take in the numerator side. So what will happen to the formula? You see, xu max by d equal to 0.0035 into Es divided by 0.0055 Es plus 0.87 Fy. Okay, now we can substitute the value of Es, that is 2 into 10 to the power 5 Newton per mm square. We will get formula of xu max by d. I will write here xu max by d equal to 0.0035 into Es, it will give you 700. Okay, divided by 0.0055 into Es, it will give you 1100 plus 0.87 Fy, and this formula we have to insert in the cell. I will tell you how to insert that. Okay, so we have xu max by d, we can take this in the subscript side. Subscript, okay, by small d, by small d, xu max by d. I will take this part, subscript. Okay, xu max by d equal to 700, okay, divided by what you have 1100 plus plus 0.87 Fy, 0.87 Fy, 0.87 into Fy. So where is Fy? You see it is in the given data Fy. Okay, so got the value of XU max by D, but we want in 2 digit, and we can use roundup function here. Round up we got 0.48. The formula for QLIM is QLIM equal to 0.36 FCK XU max by D into 1 minus bracket 1 minus 0.42 XU max by D. We shall insert this formula in this cell. We will see how to do that. Equal to 0.36 into FCK. We have FCK in the given data. FCK into XU max by D. XU max by D is here. Okay. Into bracket 1 minus, again we shall take bracket 1 minus 0.42 into XU max by D. XU max by D. So here we will take bracket 2.7593. We can round up this value comma 2.76. The formula of MULIM is MULIM equal to QLIM into BD square. This formula we have to insert in the cell. Equal to QLIM into B into D square, small d square, into D into D. And you see the B and D are in mm. We have to convert that into meter, and we want moment MULIM in kilonewton meter. For that we have to divide it by 10 raised to 6. 10 raised to 6. 171.04, and we can round up this value up to 2 digit. Okay, sorry, it is up to 2 digit. We don't have to round up this. Here they are asking us to design a doubly reinforced beam. That does not mean that directly we have to go for design of doubly reinforced beam. It depends on some condition. What is that condition? I will tell you. If MU is greater than MULIM, MU is the applied moment. If that MU is greater than MULIM, then we have to go for doubly reinforced beam design. Okay. Else, if MU is less than MULIM, then we have to go for singly reinforced beam design. So we have to check whether MU is greater than MULIM or less than MULIM. Depending on that condition, we will design a beam, doubly reinforced beam or singly reinforced beam. And you see MU is given here. Here we can easily see MU is factored bending moment. MU is greater than MULIM. Okay, so here we have to go for doubly reinforced beam design, but we need to see how to write the conditional statement in the Excel it can happen that mu shall be less than mu lim, then there has to be some statement that indicating we have to go for singly reinforced beam design. So I will write the conditional statement here by using if function. Okay, if mu, this is mu is greater than mu lim, then we need to go for, since mu is greater than mu lim, go for doubly reinforced beam design, okay. Or else, since mu, if this condition is not satisfied, then mu will be less than mu lim, then go for singly reinforced beam design. Okay, go for singly reinforced beam design. Okay, so directly we have this statement mu is greater than mu lim. We can just edit here mu lim. Okay, mu is greater than mu lim, then we have to go for doubly reinforced beam design. If you change the load, for example, instead of 30, if I take 15 here, then you see what is happening. The mu value is 146 and mu lim is 171.04, and you see directly automatically the statement is changing. Okay, since mu is less than mu lim, go for doubly reinforced beam design. We shall take what we have given here. We will change this to 30, then mu will be greater than mu lim, then we have to go for doubly reinforced beam design. Now we will deal with the design of tensile reinforcement. You see that we are dealing with simply supported beam. In simply supported beam, the tensile reinforcement are provided at the bottom because tension is at the bottom. And you also see that we are dealing with doubly reinforced beam design. In doubly reinforced beam design, AST, the area of tensile reinforcement, is bifurcated or divided into two parts, that is AST1 plus AST2. We have to find AST1 and AST2, then combine them, we will get the area of tensile reinforcement. AST1 is associated with the limiting section. Uh, Balanced section is called as limiting section in case of limit state method, and it is also called as AST-LIM. Okay, so AST-LIM formula is given here, AST2 formula is given here. We are required to insert this formula in our Excel sheet. You see that we have rearranged the formula in the denominator. We have taken a D out of the bracket, and this the formula that we are getting. We are required to insert this formula in our Excel sheet. Okay, AST AST1 or AST-LIM equal to, you see that the area of reinforcement, we want area of reinforcement in mm square, and mu-LIM is in kilonewton meter. We have to convert kilonewton meter into Newton mm. It can be done by multiplying it by 10 raised to 6. Okay, so bracket mu into 10 to the power 6, 10 to the power 6, you can do in this way, divided by 0.87 into Fy grade of steel into you can see the formula, into effective depth. We have effective depth into bracket 1 minus 1 minus xu max, 1 minus 0.42 xu max by d, 1 minus 0.42 into xu max by d, xu max by d we have here, xu max by d bracket close. one more bracket we have to take here. Okay, so this is the AST1. We got AST1 and it is in mm square. Okay, now we will go for AST2. AST2. Before going for AST2, you see in AST2 we have D dash. And what is D dash? I will tell you. You know D is the effective depth of the beam, and D dash is nothing but effective cover of compression reinforcement. Effective cover of compression reinforcement. D dash is nothing but distance of the centroid distance of compression reinforcement from top of the beam, or you can say that it's a distance from the top of the beam to the center of the compression steel. Okay, so you have to add the clear cover plus diameter of the ring and plus half of the diameter of compression steel. Here I have written d dash equal to clear cover plus diameter of the ring, diameter of the stirrups plus half of the diameter of the compression steel. Okay, uh, in that we have to define the what is the diameter of the compression steel. Diameter of the compression steel, diameter of the compression steel, we shall take it as 16 mm. And now we can find d dash equal to clear cover. Clear cover is given in the data. Clear cover plus diameter of the ring, that is 8 mm, plus half of the diameter of compression steel. Half of the diameter of the compression steel, 16 divided by 2 bracket close. So this is what the effective cover for compression steel. Okay, now we can find AST2. AST2 equal to, again you see the formula, it is mu2 divided by 0.87 fy bracket d minus d dash. Okay, what is mu2? Mu2 is nothing but mu minus mu lim. Mu minus mu lim, again it has to be converted into Newton mm. Okay, mu, what is mu? Take bracket here. Mu is the applied bending moment. Okay, minus mu lim. Okay, and whole thing has to be multiplied to 10 raised to the power 6, because we want to convert that into Newton mm, 10 to the power 6. Okay, 10 to the power 6. Then we can divide it by the denominator. What is in the denominator? 0.87 Fy d minus d dash. 0.87 Fy, 0.87 grade of steel. Grade of steel is 415 into into d minus d dash. One more bracket we will take here, d minus d dash. Bracket close. So we got AST2 mm square. Okay, copy this. AST, area of tensile reinforcement, it is equal to AST1 plus AST2. So this is how we calculate area of tensile reinforcement. We got the AST required, how many area of reinforcement we have to provide, that value we got. Based on this value we have to provide number of bars. Already we have defined the diameter of tensile reinforcement, that is 25 mm. First we need to find how many bars are required for this area, and then accordingly we have to provide the number of bars. First we will have to find number of bars required. Here I have given the formula. Number of bars required equal to AST divided by area of each bar. AST, this is the AST divided by area of each bar. The area of bar is pi by 4 into d square. We can take the value of pi 3.142. 3.142 divided by 4. You can take this in bracket into d square. 25 into 25. 25 into 25. Okay, bracket close. So number of bars required are 3.929, and you cannot provide the bars in digit. You can provide bars in 1, 2, 3 numbers, but you cannot provide in digit. We have to round up this value to a higher number. Number of bars provided equal to round up function. Take this value comma 0, because we don't want anything in digit. Number of bars provided are 4, and now we can find the AST provided, because AST provided and AST required will be different. The provided will be more than the required. So AST provided equal to number of bars provided into area of each bar. AST provided equal to 4 into area of each bar, not into, okay, into, this is into 3.142 divided by 4 into d square. 25 into 25. So this is the value of AST provided, square. We can also find the percentage of reinforcement provided, percentage of steel. We get the use of this in when we are dealing with the design of shear. PT percentage of steel equal to, we can refer the formula AST provided divided by BD into 100. AST provided can take in bracket AST provided divided by B into D. B is width of the beam into small d into D, bracket close. One more bracket we have to close here, okay, into 100. So this is the percentage of reinforcement provided. After determining the tensile reinforcement, we have to write a statement indicating the number of bars and the diameter of the bar through the function of Excel. I will show you the formula. We have to use this concatenate function. Under this, you have to link the variables, and whatever the statement you want to write, you can write the statement under the double inverted comma. Here I have written hence provide is the statement that I want, and the number of bars is the variable that I have to link, and the diameter of bar is also the other variable that I have to link. You see how to do that. Equal to sign concatenate double inverted comma hence provide double inverted comma now we have to link a variable, hence provide 4 bars, okay, 4 bars comma double inverted. Now you see the statement, number of bars is linked. This is a statement double inverted comma, we have statement bars of double inverted comma next variable is the diameter of the bar, that is 25 square, okay, 25 square. one more statement we need to add, double inverted comma, diameter, double inverted comma. So we have this statement. Automatically, whatever the number of bars will be there, it will take the number of bars, and even if you change the diameter, here the change will be reflected. Now we will see determination of compression reinforcement. These are the things that we need to determine compression steel. D dash by D, FSC, ASC. ASC is area of compression steel. FSC is the compression stress in compression steel. To determine FSC, we need to determine D dash by D, and you see FSC from this table we shall be calculating the value of FSC, we shall be taking the value of FSC. FSC depends on two factors. It depends on grade of steel, and it also depends on D dash by D ratio. Okay, so to find FSC we have to calculate the value of D dash by D. When you are calculating the value of D dash by D, you need to take care that the value of D dash by D should be only in this range. You must get the exact value of D dash by D to take out the FSC value. You should be getting 0.05, 0.1, 0.15, 0.2, or you can say you should be getting the value in the range of 0.05, like 0.05, 0.1, 0.15, 0.2. To get in that range, we can use m roundup function. Okay, you can take bracket D dash is the effective cover to the compression steel divided by effective depth, that is D. Okay, comma, bracket close, comma, 0.05. You see you are getting the value of D dash by D in 0.05 range. If the value is changed, then you will be getting 0.05, 0.1, 0.15 in that range only. Now we can calculate the value of FSC. To find the value of FSC in Excel, we have to use VLOOKUP function. When we are using VLOOKUP function, we have to provide the lookup value. In our case, we are looking the value of FSC from the table. For that, we have to provide the lookup value as FY. For FY value, we are looking for FSC value. Okay, so you can assign the FY value from the given data. But you have a problem here. See, if FY is 415, you have 4 different value of FSC, and that depends on the D dash by D ratio. Okay, so when you are using only VLOOKUP function, you also have to assign the name of the column, whether you are taking the value from J column, K column, L column, M column, whatever column that you will be defining, the FSC value will be extracted from that column. But we want the value of FSC to the grade of steel and also to the D dash by D ratio. So when you are using VLOOKUP plus match function, in that function you don't have to define the value. When you are using only VLOOKUP function, then you have to define the name of the column. But when you are using VLOOKUP plus match function, you are not required to define the name of the column. I will show you how to use that. VLOOKUP, for which value you are looking up. Lookup value you have to provide the grade of steel. From the given data you have to take the grade of steel. Okay, then you have to select this entire table, comma, match, for which value you are matching up. You also have to match this value of D dash by D. From here you can take comma, different value of D dash by D. You have to select the entire row. Okay, comma, 0 for exact match. comma 0. Now you see you are getting 353. Our Fi value is 415 and d dash by d is 0.1. So exact value of FSC we are getting 353. If your d dash by d is 0.15, then you shall be getting 342 value. Okay. So in this way we can determine FSC value. Now we can discuss how to find the area of compression steel. First we need to write the formula of ASC. ASC equal to mu2 divided by FSC into d minus d dash. This is the formula by which we can find ASC. We will see how to find ASC. mu2 we don't have the value of mu2. mu2 is nothing but mu minus mu lim. Okay, so ASC equal to mu mu minus mu lim in bracket we can write it down into 10 to the power 3, sorry, 10 to the power 6 into 10 to the power 6. Again one more bracket we can take here, divided by FSC into divided by bracket FSC. FSC value we know, FSC into bracket d minus d dash. D is the effective depth minus d dash. D dash is the effective cover to the compression steel. So here we are getting 644.62 mm square as a compression reinforcement. Now we can assume the diameter of the compression steel, that is 16 mm. We can find the number of bars that are required. Number of bars equal to AST divided by area of each bar. 3.142 divided by 4 into 16 into 16, sorry, 16 into 16. Okay, we are getting 3.20 as number of bar. We can do round up this value to a regular value, comma 0. We are getting 4 bars of 16 mm diameter as a compression steel. You see, we have designed the tensile reinforcement, that is 4 bars of 25 mm diameter, and we have also designed the compression reinforcement, that is 4 bars of 16 mm diameter. We can provide a statement here. Hence 4 bars. We can use the concatenate function, double inverted comma, hence provide comma 4 bars of 16 mm diameter. Four bars. Okay, here we have bars of can provide some space. So in this way we have to design for the compression reinforcement and for the tensile reinforcement. You see, we have designed for the tensile reinforcement, and we have also designed for the compression steel, and design for shear. I will cover this in the next video. That will be the part 2 of this the in continuation with this video. In design for shear, we need to cover this. Already I have designed the shear, and finally we have to end up like this, providing bars at the bottom, providing bars at the top. Then we have to provide two legged stirrups. The design for shear I will cover in the next video. Thank you for watching this video. Thank you very much.